these great results about in average case complexity. And he showed that if NP can be efficiently solved on average by deterministic algorithms, then we can solve UP in deterministic time 2 to the n divided by log n in the worst case. And in his later work with Mikito Larashima, from the same assumption, they show that we can learn small circuits on any unknown p-poly sampleable distributions. I know that neither of these results says anything about Kolmogorov complexity, but the proofs heavily rely on time-bounded Kolmogorov complexity, and more specifically KT. And in both cases, we need to assume that NP can be solved on average by deterministic algorithms. And if we just assume that NP can be solved by a randomized algorithm, the proof no longer works. And the reason is that the proofs are long black box. If we just replace a deterministic average algorithm by a randomized average case algorithm, then we cannot just use as a black box and get the same thing. So the question here is whether we can extend it to the randomized setting. There are good reasons to consider randomized average case complexity and not just the deterministic one, but I will not get into the details. And in the same paper where we introduced the notion of PKT, we also use this notion to extend the previous result to the randomized setting. So we show that if NP can be efficiently solved on average by a randomized algorithm, then we can still get a faster algorithm, a faster randomized algorithm that solves UP. And we also get exactly the exact same learning consequence as in previous work. Okay, next, I'm going to talk about some of the very important properties of Kolmogorov complexity. And one such property is called the coding theorem. So the coding theorem for time-bounded Kolmogorov complexity says that if you have computable distribution D that samples X with probability D of X, then the Kolmogorov complexity of X is at most log 1 over D of X. And the proof of the coding theorem crucially relies on the time-unbounded feature of Kolmogorov complexity. So the question here is whether there's a coding theorem for time-bounded Kolmogorov complexity, say K-poly. Say we want to show that there's if we have efficiently sampleable distribution D that samples X with probability D of X, can we say that the K-poly complexity of X is at most log 1 over D of X? And in fact, Antunes and Fortlau showed that this is true if we assume a strong de-randomization assumption, but this result is conditional. And in a joint work with Igor Oliveira and Marius Zeman, we get an unconditional coding theorem for PK poly. So if there's an efficient sampleable distribution D that samples X with probability of X, then we can say that the PK poly complexity of X is at most log 1 over D of X. And we can also show a converse. So the efficient sampleability of a string corresponds exactly to its PK poly complexity. Yeah. And okay, another important property in Kolmogorov complexity is called symmetry of information. So we know that for string X and Y, the Kolmogorov complexity of X and Y is roughly at most the Kolmogorov complexity of X plus the Kolmogorov complexity of Y given X. And this is just because if we want to get a program that prints X and Y, then we can first use a program that prints X, and then use a program that prints Y given X. And symmetry of information for time-unbounded Kolmogorov complexity basically says that this inequality is tight in the sense that K of X and Y is at least K of X plus K of Y given X minus some small term. And the reason why we call it symmetry of information is because from the two inequality, we can get something that's analogous to what's called symmetry of information in Shannon's information theory. And again, the question here is, does symmetry of information hold in the time-bounded setting, say for KT? And unlike the coding theorem, we know that symmetry of information is unlikely to hold for KT. And that's because we know that if one-way function exists, then symmetry of information for KT fails. And intuitively, if we have a one-way function f, or let's say if we have a one-way permutation, then from x, we can compute f of x efficiently. But if we are just given f of x, we cannot get back x efficiently. So there's an asymmetry of information between these two strings if we take into account the time. And Longrad and Watanabe formally connects the existence of one-way function to the value of symmetry of information for KT. But the results only shows one directions. And since then has been an open question whether we can get some if and only if statement between one-way functions and symmetry of information. And in an upcoming work with Shuichi Hirahara, Rahul Ilango, Mikito Larashima, and Igor Oliveira, we show that one-way function exists if and only if some average case version of symmetry information for PKT does not hold. So again, PKT seems to be the right notion to connect the one-way function and symmetry of information. And in the same paper, we also use other properties of PKT to characterize more complexity assumptions, such as P log equals to NP or NP star on average. And there will be a talk on this in the upcoming workshop of the meta complexity program.
Any questions? I'll ask a sort of naive question. So your new condition on equivalence of one-way functions, how does it relate to the average case hardness of CKT or something? Is it in the same spirit?
You mean the last one?
Yeah, because there are some other theorems like this, right? Like the Liu pass theorems and so on.
Yeah, first of all, it's unconditional. So the equivalence is unconditional. And compared to Liu pass says that one-way function exists if like KT is hard on average. And in this case, we are not considering like the hardness of computing some problem. We consider whether the properties of PKT holds, whether properties of time-bounded complexity holds. And so in some sense, it's like different.
Function when you assume that the symmetry of information does not hold.
So the question is, what's the construction, the arrow going the other way? So if you assume the symmetry fails, then is there a simple way to describe the one-way function construction? Maybe you can take it offline.
Probably we should take it off.
Right. So let's take a coffee break now, and we'll resume at 11:30. And let's thank all the speakers in this session.